So now I come to the main theorem in this section is that the set of smooth points phi is a open subset. So theorem X smooth, which is all the points in X. X is smooth. Or capital, I write capital X is smooth at X. X is any variety, yeah. X is any algebraic variety. Is an open subset. Is a non-empty open subset. Yeah, assume it's separated, pre-variety. So assume separated. Possibly.
Smooth at a point will be smooth about a neighborhood or
Yes. Or in other words, the singular set is a closed subset, proper closed subset. So singular set, they are, and the non-smooth point, there is the dimension should be less than the underlying variety. So most points are smooth points. The non-smooth point, they are special. The singular points, they are special. Okay. So first of all, these regular local rings, these are integral domains. This is, I don't know whether in commutative algebra you have seen this result. Okay. So this is so see, the point is that X is proof without, so I want to reduce it to the case when X is a hypersurface. From any variety. First of all, if you write X is X, you can write it as some union affines. Right. So then what I am saying that X minus X smooth, I can write it as union of Xi intersection Xj, I not equal to J, union Xi minus Xi smooth. I mean, of course, there will be another Y. So without loss of generality, I can assume X is affine. I prove that this is closed. This is open. Sorry, this is closed. This is closed will imply that X minus X, the non-smooth points of X are closed. So enough to, so without loss of generality, one can assume X is affine, right? Okay, now one fact I need to, okay, so let R equal to dimension of X. So X is affine, so suppose Ix is given by some, so I consider the ideal. So R is, so X is in some AN, affine. Then Ix is some a bunch of polynomials, say F1, F2, Fl. Now, what is the time? P, now, P, take a point P belongs to X. Then, what is Tp of X? By definition, this is set of all points A1, A2, An such that summation del Fi del Xj at P Ai equal to 0. Sorry, not Ai, Aj. J equal to 1 to N. And now Fi's are the I equal to 1 to L. Right? By the proposition. Now see dimension. So this dimension of X is R. So that means that this is the dimension of OXP, right? It's a irreducible. So OXP, dimension of OX is same as dimension of OXP. Dimension of the local ring is same as the dimension of the ambient variety. So that will say there's a dimension of Tp of X. So P is a smooth point. P is a smooth point. P is smooth. This is same as saying that dimension of Tpx is equal to R, or which is same as less than equal to R. The dimension of Tpx is always greater than equal to R. Now, if it is a smooth point, then dimension of Tpx should be less than equal to R. Right? Less than equal to R means it is always greater than equal to R. So, if I is less than equal to R means this is equal to R. So, this is same as saying in terms of the Jacobian, the rank of the matrix del Fi del Xj at P is greater than equal to N minus R. But rank of a matrix greater than equal to N minus R is an open condition. So, this implies that the smooth point, so rank of any, if you have a matrix, rank of the matrix is some greater than, this is an open condition, because some non-zero of the minors. Non-zeroness is some polynomial equation. Minors, they are determinant of some smaller rank matrices, and that's a polynomial. So, something is non-zero is an open condition. So, that's why, so this is this implies that X smooth is an open subset. So, but the point is that but why this is non-empty? You still have to prove that there is at least one point. You know, okay, some abstract way you are defining this is a open subset, but why it is a non-empty? So, you have to prove something, that there is a smooth point at least, even in affine case. So, here if X is affine, I am saying that I can reduce it to the hyperplane hypersurface section. So, now this is a result that any affine variety is birational to some hypersurface. So, I have not done this but I use this a result which I will do it later. I will leave it as exercise. If X is affine, X is birational to a hypersurface. Huh? Birationality, yes, I'll define that. So suppose X is a X is affine of n dimension n, dimension of X is n, and this is hypersurface in n plus 1. Say. Yes. Hypersurface in n plus 1 means dimension n, right? So this is a proposition or exercise. I'll leave it as exercise. I'll use this. So what is birational means X and Y are birational. So I write it with that dotted arrow, X to Y. If there is a open subset here, non-empty open subset, U and V, such that when you restrict this F restrict to U, this is isomorphism. Example, N and Pn, they are birational. Because Pn is, you have an open subset which is isomorphic. There are many, the standard open subsets. These are all birational, An, Pn. And this is the equivalence relation, that if X is birational to Y, Y is birational to Z, then X is birational to Z. So this is a coarser classification. See, you say X and Y are isomorphic, but this is a weaker classification of algebraic varieties. So that is known as birational classification of algebraic varieties. When you many invariants. For example, the function failed. Function fields are isomorphic. Yeah, there is another way of saying. If it is, but this is another way of saying that U and V, if you have an open subset U in X and V in Y, such that they are isomorphic. They are not very bad, they are not very different from each other. At least on an open subset, they are the same. So these are called birational. Now the point is that X is affine. If X is affine, then X is birational to a hypersurface. Now if I prove that for a hypersurface, there are smooth points, and under isomorphism, smooth points goes to smooth point. So it is enough to prove that when X is a hypersurface, the set of all smooth, there is a one smooth point. Because after all, this is an open subset, and this hypersurface, that open subset will go to an open subset in X, and because it's isomorphism, isomorphism will take smooth points of the hypersurface to the smooth point of the underlying variety. So it is enough. Now you can reduce, so for non-emptiness, you can reduce X is hypersurface in some n plus 1 of dimension n. So by the argument of birationality, X is X, we can assume this is non-emptiness result, for non-empty, non-emptiness of smooth points. X is an hypersurface. In an plus 1. So X is some V of F. Now if I take a point P in X, then this is a singular point, or it is a non-smooth point. Means what? That means del F del Xi equal to 0 for all I at the point P. But this AF without loss of generality, you can assume that AF is a radical ideal. By no senses, because F is a radical ideal means this is the smallest degree polynomial such that 0 set of X is 0 set of that F. So now del F, now since F is a non-zero, so one of this del F X del Xi is non-zero, because after all F is a polynomial. F is not a constant. If it is, right? If it is, because x is given by a hypersurface, so f is not constant. One of the del f del xi is non-zero, but then p satisfy the x satisfies the equation. The del f del xi of p is 0 for all p. So that, but del f del xi degree is less than the degree of f. But f is a radical idea, so it is not possible. So only possibility, so this will imply that del f del xi is 0. But in characteristic 0, this is not possible because of this degree argument. But in characteristic p, you can have polynomial like some power of p, gx. So what I am saying that then f will be given by some gx of power of p. But again, f is a radical ideal. F cannot be of this form. So del f del x is 0, but f is non-zero, can happen only in this way, in characteristic p. Huh? Huh? Because what is definition of a radical of a f square? Same as radical of f, right? So when you say radical ideal, means that is if some power is there, that has to be there. So it cannot be some power of gx power p. So what is radical of gx power p? It is nothing but it is gx, right? So f cannot be of that form, gx power p. Yes. There is only one polynomial because this is a hypersurface. So it cannot be of this form because this is a radical ideal, and that is true for characteristic p also, algebraically closed field. So because this is a radical, so this cannot happen. So hence you have a point which is smooth. So now you prove it for the complete.